Hey everybody, and welcome to a new video. So in this one we are going to see how to realize this effect. Okay, so let's start from scratch. I'm going to keep this patch here because sadly here I don't have a second screen, so I will need to pick at this patch once in a while. Let's just stop it. Just make the window visible, not invisible, and let's create a new one. Cool, so I created this effect actually inspired from my own work Anthropocene, and also this was itself inspired by the work of Hiroichi Kurokawa, which often uses this line, especially in the works from some years ago, in which he connects pixels from videos using these lines. So I'm not sure I can show you the videos because of copyright reasons, but I can put the links in the description. So we are going to realize a similar effect in Max. So first of all, let's save the patch. Let's call it lines K as Kurokawa tutor. Put it on the desktop. And cool, first thing we need a JIT world. Let's call it lines, shift lines. And let's give it floating 1, the usual stuff, size of the window 320 by 240, erase color black. And then let's give it also ortho 2 because we want to work with all in 2 dimensions. We don't want to have a zeta dimension, so we actually will want to have ortho 2. And let's create a toggle here to activate and stop the world from rendering. Cool, now we need a JIT movie object. We are not going to use the output texture attribute because we are working on the CPU with this algorithm, okay? So this whole algorithm works on the CPU. Maybe I'll do a GPU version in the future, but for the moment it is on the CPU. So in order to be extremely clear, let's actually put output texture 0. Cool, let's put volume 0 because we don't want to be bothered from the sounds of the movie. And let's create a receiver for the metro, which we're going to send from the JIT world. So here, let's create a sender. Let's create the usual JIT FPS GUI to check our frame rate. Cool, and let's maybe start with a file. Let's start with a bball.mov. So movie file bball.mov. I think that's the name. Okay, cool. Let's see if we got the actual movie. And we don't have it because the world is off. Okay, cool. So we got the movie. Now what we want to do is to transform this movie into black and white and in a one-dimensional matrix. So we can do that using RGB to Luma, this simple object here. We could maybe also decide to reduce the dimensions of this movie before we do that. So to be sure that actually the dimensions will stay small. And we are going to adapt the X dimension to the resolution of the movie. So the Y dimension is always going to be 300, but the X dimension is going to be adapted by the resolution of the movie. So what we need to do, first of all, once we read the movie, inside, is to get the dimensions of this movie. So let's say that we put a movie inside the JIT movie object, root, read, okay, we get the name of the movie and the number 1, which means the reading process was successful. Okay, so we can use then the echils1, so it's basically like the slice, but from the right output is going to give us the last component of the list that came inside. So let's try. Okay, cool, so we get the 1 here, let's say select 1, and then let's say get dimensions. So once we read the movie, then we want to get the dimensions of this movie, and let's root them here from the root. So we should be able to get the dimensions of the movie. Let's do it again. Okay, cool. So these are the dimensions of the movie we just loaded. Let's get the ratio of those dimensions. So we basically divide the X by the Y. And then what I want to do is to multiply this by 300, which is our Y dimension. And this is going to be our X dimension. So let's do something like this. We could also set it to an integer using simply an integer box, and it's going to be the dimensions of our matrix. So let's check this out. Let's get the movie, let's put it here. Okay, so this is going to be 400 by 300, which is 400 divided 300 is 1.3333, which is the same ratio of the original movie, because the original movie is 320 by 240. So yeah, we actually still preserve the original ratio, but we have our desired dimension for the matrix which we are going to use to work. Okay, so very well. Okay, cool. So let's see if we get our movie in black and white, first of all. In the meanwhile, I create a JIT-gen. So let's check this out. Okay, so here's our movie in black and white. Cool. Okay, so once inside this JIT-gen, we want to check which pixels are above a certain threshold. So let's actually create a parameter. Let's call it trash. Let's give it a value. Where is it? Okay. Let's call it trash. Let's give it a value, I don't know, 0.3. And then let's say, is this greater than threshold? We simply do something like that. Very easy. So let's check with the GPU window then what we get. Okay, we get all the pixels that are above this threshold. We can also say, maybe in this case it's better to say less than threshold, or we can do something like this. We can say one. We can say both. We can choose between greater than threshold or less than threshold. So we can do something like param switch trash. Can set it to 0, and then we can say okay. If this is greater than threshold, then value true. If it's smaller than threshold, then we will choose 0. By default is 0, so by default we are working with the values that are smaller than the threshold, which for this video is the best option. So let's create a couple of messages to control those parameters. Trash here. And switch, whoops, and switch trash. Yeah, already Max is suggesting me that, very cool. Cool, so we can change the threshold here, right? It actually just needs to go between 0 and 1, because the numbers are never going to be bigger than 1 is more than 0. So very cool. If we actually can use a toggle for the switch threshold thing. Suck. Okay, very well. Cool. Then we're going to use an object from the X-ray package, which is the infamous X-ray JIT cell cores. So how does this work? It sees which are the pixels that have a value of 1, so the one that are above or less than our threshold, and then it gives us the coordinate for those pixels, okay? So it's just a bunch of coordinates in a one-dimensional matrix. Okay, so very nice. Now that we got those coordinates, we actually need to remap them in order to fit our 3D world, because we are going to use those coordinates with a GGL mesh to draw the lines between the pixels. Alright, so what we need to do is create a JIT-gen, let's give it a title, let's call it remap. And what we need to do is to first transpose those coordinates between 0 and 1. Yeah, this is what we're going to do. So in order to do that, we need to get the dimensions of our matrix. So the dimensions, we're gonna get them from this message here, because these are the actual dimensions of the matrix. So let's create a parameter, matrix dim, let's give it a default value of 10 by 10, just, we don't care. And yeah, let's do like this, $1 and 300, cool. So it's basically the same, but we're using this as the matrix dimension for in order to divide the coordinates that we get from the X-ray JIT cell core object. Let's actually set the output type as float. So out mode 1, I believe, is the one that will give us the float output. Let's check. Out mode 1, yeah, perfect. Okay, cool, so now we have output in float. I'm not sure if it matters, but I just wanted to do that. Cool, so now what we do, let's divide actually the coordinates by matrix D minus 1. So both for the x and the y we get the values minus 1. Why minus 1? Because the dimensions, the coordinates will go from 0 to the dimensions minus 1. So this is what we need to get them in the range 0 to 1. Cool. Then let's actually scale 0 to 1, minus 1, 1. So we get them in the range minus 1 to 1. Cool, let's actually check already how this is looking. So let's create a JIT-GL mesh. How did I call these lines? Draw mode lines. Color, let's make it completely white. And cool. Let's check these out. Okay, so what are we getting? Oh, of course, we need to actually send the dimensions of the video. So let's do like this. Let's type here 400. Okay, good. We are getting it. Just as you can see, the y is reversed. So we actually need to reverse the y here. So let's actually switch the x. Let's switch the y. And we're going to multiply the x by the ratio in order to have the lines also correct in respect to the ratio. And now we are going to the proportions of the movie, and then we are going to multiply the y by minus 1. So let's create a vector. So this is going to be the x, this is going to be the y, and we have to retype inside the dimensions. Okay, so now at least the y is correct. So what we want to do now is to multiply the the x, sorry, by the value, the ratio of the matrix dimensions. So let's actually do like this, switch x, switch y from the dimensions, actually divide the x by the y, and let's multiply these by our x value, x coordinate. Okay, cool. So let's check now. This should be the proportions should be now correct. In fact, it looks pretty cool. It looks pretty good. Okay, so now we go into the actual meat of the algorithm, which is to select randomly the vertices that we just got, the coordinates, in order to connect the lines, not just one vertex after the other, but in a random way. Okay, cool. So let's use another JIT-gen to do that. Let's create a title. Let's call it Scramble. And let's connect these here. Cool. We will use a JIT noise matrix in order to do that. So we need a JIT noise matrix with two planes, float 32, and the dimensions of this noise are going to be the dimensions of the matrix that we get out of X-rate JIT cell cards. So let's actually use JIT.matrixInfo in order to get the dimensions. So let's send it here. Let's root dimensions. Let's see if we get the actual dimensions of this matrix. Okay, cool. So we can then prepend dim, and we can connect these to the JIT noise. So now this JIT noise is the same exact dimensions that the matrix that we get out of JIT cell code, which is also the matrix that is worked by those JIT gens. Cool. So let's connect these here. So now what we can do is simply using nearest. So what we're going to do in this way is actually sample those vertices according to some random numbers. So we actually forgot to bang the noise. So first we send the list with the dimensions, and then we actually bang the noise. So as you can see now, the vertices are being connected in a random way, right? Which is not exactly super cool. It's a bit different from the result that we saw in the beginning. So what we want to do is to actually check that if the vertices are close enough, then they get connected. Otherwise, they will not get connected. But how can we make sure that they are close enough? Well, in order to do that, we need to check if this vertex is going to be close enough to the next vertex. And how do we know which one is the next vertex? Well, in order to know that, we actually need to sample the noise and check the next value that the noise would have captured. This is going to be clear in 1 second. Okay, so let's create another nearest object. And this nearest object is going to take as well the input, but sampled at a different position. Then we simply check the distance between those two vertices. We say, is this less than our threshold? And let's create a parameter called threshold. Let's give it a value, I don't know, 0.3. So, okay, if this is less than our threshold, then output the actual pixel. So value if this is true. And if it's false, just output the position 0.0. Or we can actually also send these away by outputting the position 1000, 1000, which will be away from the screen. Okay, cool. But as you can see, now for the moment, let's keep it at 0, 0. So the problem now is that if we sample them at the same pixels, yeah, of course, their length is going to be less than the threshold because it's the exact same vertex. So what we need to do is to check the next value of the noise. So in order to do that, we are going to use the nearest pix sampler. So the nearest pix, as we saw in the GGen tutorials, basically takes the value of the input matrix according to some integer coordinates. Cool. So what we're going to do is going to use a cell. And we're going to check the pixel that is next in line. So +1, 0. So the pixel that is next in line, it's going to sample the next cell, and the current value of the noise is going to sample this cell. But there is an error here with this code, which is, before we test for the threshold, we need to transform this number into a scalar, because for the moment this is a vector with 2 components. So in order to transform this into a scalar, we can use, for example, the length to check the length of the vector. So as you can see now, the cells are being connected. Some are going to be connected to the next pixel, but some are just going to be connected to the center. Why is that? Because, let's make a little drawing. So let's say that we are working with this cell here. We are just checking for the next cell. So, okay, let's say that the length between these two cells is smaller than our threshold. Okay, so they are going to be connected. But then for this cell, if the length of the distance between these two cells is bigger than our threshold, that this is not going to be connected. So this is going to end up at the value 0. It's going to be connected with the vertex 0. So actually what we want to do is to check first with this cell if it's close enough to the next cell, and then with this cell to check if it's close enough with the cell that was before this. Okay, so we can do this in a very simple way. Let's actually first just switch the x, because we're just is anyway a one-dimensional matrix. So let's say sample the next cell with +1, or sample the cell before with -1. We have to decide when we want to sample the next cell and when we want to sample the previous one. So let's say we are at the first cell of the matrix. Of course, we want to sample the next one. But let's say we are then at the second one, and we want to sample the previous one. So we could use, for example, the modulo 2 of the x cells, the x dimensions of the cells. So for example, when this index is 0, this is going to be 0. When this index is 1, the result of the modulo is going to be 1. So we say when this is 1, then check the previous cell. And then again, this is going to be 0, this is going to be 1, because we're going to do a modulo 2. So we can do something like that. So let's check. Let's use the modulo 2. And then we can use the switch operators. So condition to test. When this is true, then we want actually to use -1. When this is false, we want to use 1. So let's arrange them a bit better. Okay, like this. And let's check this now. Okay, cool. So this was the key to actually realize our effect. We can now connect these and have the vertices that are not connected simply to disappear outside in the world. And cool, we can now check our threshold. This is actually a length threshold, so len thresh, because this is the threshold of the distance between the pixel that must be connected. So let's create message with this. Let's connect this here. And we can then experiment a bit and play around with different length. The more bigger is this threshold, the more vertices are going to be connected, of course. So okay, this is actually the main thing of the algorithm. Then you can embellish it a bit by superimposing the video as well on the screen and filtering it out with a similar system to our threshold here. But this is the more kind of the real part of the algorithm. So we will not go any further with that because this is it. Okay, so thank you very much for following. As always, this video is going to be available just now for my Patreons, and it's going to be available for everybody in 1 week. So thank you for following, and see you soon with the next video, which is probably going to be about particles. We will go on with the particle series and start to work with the transform feedback. Okay, so see you soon. Ciao.